is called sequencing, right? So there are a lot of different varieties of sequencing, n machines and n jobs, and two machines and n jobs, three machines, n jobs, and so on. So first is the simplest thing. It's called n jobs and two machine. It's a simplified sequencing problem. It is such a way that like we have got only two machines, machine A and B. That is both used for the 5 jobs. It may not be a different job. Say, for example, it could be person 1, person 2, person 3, person 4, person 5. So involved in the machinery activities. So they use machine A and B, right? So both machines are used by all the people. And in fact, these are the different durations which you can use. So I have not mentioned it as in minutes or hours. So let's assume that is a minute. That's a minute, or you can even call that's time in minute. So it's a time required to do operation in that particular machine, right? For that particular job. Say the first job takes 5 minutes in machine A, whereas it takes only 2 minutes in machine B. Whereas job number 2 takes 1 minute in machine A and 6 minutes in machine B. Whereas job 3 takes 9 minutes for machine A and 7 minutes for machine B, and so on, right? So this is how it is, right? So now what we have to do is we need to formulate a sequence such a way that we allocate one job to a machine which having the least sequence or something like that, right? And before we go into that, so this is the order of the sequence. Say the order is that. So we need to do machine A, then machine B. It is not like whichever we like. Say for example, in this case, machine B has got 2 minutes duration, which is pretty much higher when compared to machine A. But then we will be doing it as in sequencing, right? So directly take this, and for this one, and for this one. It's just not like that. Say we cannot do like that, but there's a optimum way in which you can do, and that is what we're gonna focus today. And this is pretty much called as Johnson's algorithm, and like a Hungarian algorithm for assignment problems, and Johnson's algorithm is for the sequencing problem, right? So it's very simple. And like many of our examples, you don't have to make this multiple tables. For illustration, I've just made a multiple table, so you can even make this particular you can solve this particular problem with a single table itself, right? Say, so what you have to do is first recreate this particular table like this. Then you have to do this thing. Say we have got 5 jobs: job 1, job 2, job 3, job 4, and job 5, right? So we have got 5 jobs. So kindly make 5 boxes and make 5 boxes like this. Right. So initially, I have to make 5 boxes, which represents the sequencing of the activities. And the left side, you can put machine A, and right side, you can put machine B, since the order is A to B. If the order is B to A, you reverse the order. So this will be machine B, and this will be machine A, right? Say this is a simplified thing. So in order to have a clear-cut understanding of sequencing problem, I just wanted you to take this order, particular regular order. We'll also do a problem with the reversal order or the variable orders and something like that, right? Say mission A, it's from this side to this side, from mission B, from this side to this side. So what we need to do is first we need to select this, consider this as a matrix. This as a matrix, right? So you need to find out least machinery time. Say among 5, 1, 9, 3, 10, 2, 6, 7, 8, 4. The least is the 1, right? So least is the 1. That corresponds to machine A, and the job number is 2. Say you have to do is take this J2 and put it here. So the first cell got filled with J2, which means that that is corresponding to machine A, and which is having a least cost, least time, right? So once you do that, you will be discarding this particular column. The reason is that we eliminate that from the consideration, because we can assign one machine to one job only. So that's why when we know this is least, so it's impractical to have the job 2 in machine B, because it has the highest time. So the entire chunk is removed, right? Then we will have remaining 5, 9, 3, 10, 2, 7, 8, and 4. Among this, the minimum is the 2, right? So this is the 2. So that will be for machine B, job 1. So which means that our sequence will be J1 for machine B. So we don't have to put J1 here because that corresponds to machine A. So we'll go back to machine B, that particular scenario. So you fill this with J1. So which means that J2 is for machine A and J1 is for machine B. So once you make the allocation, you also remove this particular column. Right? So in this case, I've removed this particular column and we are left out with 9, 3, 10, 7, 8, and 4. So among this, the least time is 3, and that is for job 4 in machine A. So we will be putting job 4 here for machine A, right? And then once that is done, we'll be looking at this particular column and this particular column. Among this column, like 9, 10, and 7, and 4. So the minimum is 4. That is for job 4, job 5, machine B. Say I've just put job 5 and corresponding to machine B, right? So once that is removed, we will be left up with only 1. So among this, you can select which one is the least. So among 9 and 7, the 7 is the least, right? So that corresponds to machine B. So you have to put J3, which is equals to machine B, something like that, right? So once you made this necessary changes, once you make this necessary changes, you can remove this color, right? So that's that will be immaterial to us. So far we have found out corresponding stuff, but now it is just a sequence. Say we have got sequence here, which is that, like I just which is this our sequence. Say we'll perform the first operation in J2, J4, J3, J5, and J1, right? Say that's the basic logic, right? Now what we have to do is we'll take up the questions. I'll just copy this stuff. So this will be little confusing. Just kindly pay attention. Can zoom up a little bit. All right. So this is the second part of our problem. In an initial stage, what we have done is, I'll do a quick recap. So we had this problem given, and we have found out the minimum time in the matrix. Then we allocate that particular job to that particular mission. And finally, we have got this sequence, right? Say something. Now, what we will be doing that is, we will be finding out the elapsed time. Elapsed time. Then a very important concept called idle time. So far in our computation, we'll be finding even for a transportation problem, for an assignment problem, we'll find out the minimum cost or minimum time. But we haven't found out like what is the ideal time or waiting time or something like that. So this sequencing will give you that particular concept called ideal time, right? So how ideal a machine is there, like how long it's waiting for its input, or after its input, how long, I mean, after its output, how long it's waiting to get the other job done. So that's kind of analogy we'll be finding out. Then that is what basically we call a ideal time, right? Say that's called ideal time. And this is our sequence. So what we have to do is we take this particular sequence and put it here. So that's called job sequence. Then we'll have got machine A, then machine B. Then we have got time in, time out for machine A, and time in, time out for machine B, and ideal time for machine A, and ideal time for machine B. So that's basically the computational procedure for sequencing, right? So in sequencing, we have got the additional advantage of finding out the ideal time as well as the elapsed time, right? So elapsed time is the total time taken by both the machines to complete the 5 jobs. That's what we call elapsed time. You probably know that in Olympics, they call elapsed time. Like they'll check the time taken for athletes to complete 100-meter race, 200-meter race, something like that. And then if they complete, a herd of others or the record, previous record, then they can call that as Olympic record or world record or something, right? So that is what basically elapsed time. Like you can take the swimming competition in Olympics, the time they reach the destination, and that is even microsecond matters, right? So that's what basically called elapsed time. Then ideal time is like how a machine is ideal, like without its input or it just like stagnant for some period of time. So that's what basically it's called ideal time, right? Fine. So first we found out the sequence using Johnson's algorithm, right? So we say that if you do by J2 first, J4 second, and J3 third, and J5 next, and J1 at the last, you'll have a good sequencing of work to be done, right? And as I told you beginning, this is when I say it is corresponding to machine A, machine B, and this machine B. It doesn't mean that this cannot be done by machine B. So this is a procedure to find out the sequence, not the machines. In this case, we'll be allocating the jobs to the same machine based on the sequencing, right? So if you perform this different sequencing, then the time will be minimum, or the elapsed time will be minimum, as well as the ideal time is also minimum, right? So that's basically the idea, right? Say after this, probably I'll just explain this. Maybe after this, you can even try this with the regular sequence with J1, J2, J3. Then you can see appreciate the significance of the Johnson's algorithm and its forms. And say this. Probably you can take a look at that whenever you feel right. All right. So first, it's very important. Given a problem, we have found out the job sequencing. We've got J2, J4, J3, J5, and J1. Then we have got machine A and machine B, and idle time and for A and idle time for machine B. Right. Right. So pay attention. The order here is A and B, so which means that A will be the starting machine and B will be the subsequent machine or the continuation step, right? Somewhere. So a machine A, the first job, I can even call this 1, 2, 3, 4. So there are 5 jobs. This is numbering, not sequencing. Right. Right. Say this is a sequence. The first job is job number 2. Say it goes to machine A without any delay because there's no prerequisite for this. Say it can start as that point itself. So there isn't anything called waiting time, right? So it starts at 0. And J2 for machine A. Say J2 for machine A is 1 minute, right? Say the operation, the performance or the operation in machine A for job number 2 is 1 minute. So that's why the time out is 1 minute, right? Then we'll come back to machine B a little later. So we'll finish machine A. Will be time input for the next operation, right? So the next operation, job 4, is for the sequence. So for job 4 for machine A is 3 minutes. So which means that it is just like dependency. So job 4 cannot be started unless job 2 is over, and job 3 cannot start unless job 4 is over. Invariably, job 2 and job 4 has to be done prior to job 3. It's just like a prerequisite. So that's how we built the sequence. And then for only for J2, it is the 0th minute. It starts instantaneously. And then it takes 1 minute. Since machine A job 2 is 1 minute, so 0 plus 1 is 1. Then that will be the input time for the other job, that is J4, which is it starts at 1, which means that it takes after 1 minute. At 1 minute it starts, and you can see there's no waiting time or something like that. So it immediately starts. Then job 4 for machine A, job 4 for machine A is 3 minutes. So which means that it finishes by 4 minutes. The reason is that it starts at 1, then 2, 3, and 4, which means that 1 plus 3. that will become 4. So it is as simple as that. It start at first minute. It is not like 1 minute starting. It is first minute. So which means that this is, if you go from one place to another, from starting point is 0, at that time the taxi starts. And when you see somebody in the road, your friend, so you stop at that point, then that particular time. Then after you speak to them, and then you move, that is this time. So it is not like 1 minute in time, it is one first minute, the in time. Then plus 3 minutes, which means 1 plus 1 is 2, 2 plus 1 is 3, 3 plus 1 is 4. So that is what, like we have added 1 minute to this, that will become 4th minute. So that 4th minute will complete the operation for job 4, right? So that will be the input time for the next operation, which is job 3, right? So in job 3, you can take a look at for machine A, it is 9 minutes. So which means that 4 plus 9 is 13. So 5, 6, 7, 8, 9, 10, 11, 12, and 13. So that will become 13 here. So that will become 4 plus 9 is 13. And then there's no delay. You can directly put 13 here. Then for job 5 is 10 day for machine A. So 13 plus 10 is 23, right? So 13 plus 10 is 23. And you put 3 here. Yes.
Sir, how was the J2, J4, J3 sequence like selected first?
That is why I told you it's a Johnson's algorithm. This process, the output of phase 1.
Okay. Okay,
so it has got 2 phases. First, we'll be finding out the sequence, right? So this is the sequence. Then you put that sequence here. Then we'll be formulating the time. So you can see, that is why I'm saying, like, if you don't have any sequence by Johnson's algorithm, if you directly put like this, or this job as such, then you won't be getting the optimal time like this. So I'll just explain you that. Don't worry. Okay. Is it clear?
yes, sir.
Okay. Okay then. So that's how the sequence is formed based on Johnson's algorithm. Then we have got the sequencing. Then we have here like 13 plus 10 is 23. Then 23 will be in time for J1, that is job number 1. So 23 plus 5, that will become 28, right? So this is how it is made up, right? But be careful. So far so good. Since the order is A to B, so machine A, calculating the time in time out for machine A may not be very difficult. But for machine B, there's a little tricky. So kindly pay much attention. So if you don't pay much attention, this will mislead you, right? Right. So the time in for machine B is not 0. The initial job for machine B is not 0. The reason is that it will have to wait till machine A gets over, right? Say at what time the machine A, the particular job gets over, job number 2, J2 gets over is 1 minute, which means that at that instantaneously, B cannot start. So it has to wait for A to complete its operation. Then it starts. So which means that the time in for machine B is 1 minute, right? Say for example, here we have got machine A, machine B. Say this is a cutting machine and this is a painting machine. Like it cuts the stock at 1 minute. Then the painting operation has to wait till the cut is performed or the cut section is done, right? So that's basically thing. Or you can even take this as a transportation. The arrival of raw material takes 1 minute. Then only the performance or building upon the components happens. So that's why it has to wait 1 minute. Say as simple as that, right? Then for J2, the sequence for machine B is 6 minutes. Say, which means this is 1 plus 6 is 7, right? So then it is not a very big deal. Say it's quite a normal thing, right? Then you put 7 here, that will become the input time. And you should make sure that the in time of machine B should always greater than the out time of machine A. Since the order is A to B, the order is A to B. So the in time of machine B has to be greater than the out time of machine A, right? Say, which means that we have got machine A, which performs this operation. It takes 7 minutes time. So which means that the next operation, the machine A finishes is 4 minutes. So which means that it can wait till probably 7 minutes to get that particular job. Then there won't be any discrepancies, right? Then job number 4, which has got 8 duration for machine B. So in time is 7 plus the 8 will become 15, right? So in time will become 7 and out time will become 7 plus 8, that will become 15. Then we have to check the out time of machine B for job 3. The out time of machine B for A for job 3 is 13, which is less than this thing. So we can directly put here. So that's what basically it means. And next up, um, this is job 3. Kindly pay attention here. This is a very interesting thing that you should know. I'll change the color. The reason why I changed the color, I'll tell you. All right. So this is 15 for job 4, and here it is just 30. So we can directly put 15 here. But whereas job 3, here is job 3, the duration for machine B is 7. Say 15 plus 7 is 22. Whereas when you come to job 5, it takes 23 minutes to complete. I mean, it completes by 23rd minute, right? So it completes by 23rd minute. Whereas the time out for job B and the time in of job 5 cannot be 20 seconds because it itself gets over by 23 and you cannot speed up the operation to complete make it 22. So this will become 23. So that's why there's a significance that we put 23, not 22, right? Then the process is the same. 23 is job 5, which is machine B. It takes 4 minutes duration. So 23 plus 4 is 27. Whereas here is 23 and plus 5 is 28. Then 27, if you see it is less than 28, so we cannot afford to start here by 20 seconds. So that's why we would have got 27 here and 28 here. So this time we will put it here. So this time we'll put it here. Since 22 is less than 23 and 27 is less than 28. Right. So that's what basically that means. I repeat machine B because that's a little confusing. Say in the initial stage, it cannot start with 0 because it has to wait till the 1 minute is done. So that's a basic thing. So that we'll put it here. And job 2 for machine B is 6. So 1 plus 6 is 7. And we'll check here the out time for the next job, job 4 for machine is 4. So 7 is greater than 4. We can directly put 7 here. And finally, 7 plus, this is job 4. The job 4 of machine B is 8. So 7 plus 8 is 15. Then we'll check the out time of machine A for the next activity, which is job 3, which is 13. And 15 is greater than 13. So we can very well put 15 here. But machine B, job 3 is 7. So 15 plus 7 is 22. When you compare the previous, next job for machine A is 23. And you cannot afford to put it 22 here. So we'll put 23 here. Then 23 plus 4, which is the job 5's duration for machine B. So 23 plus 4 is 27. And you check the out time for machine A, which is 28, which is greater than this. So we directly put 28 here. And then 28 plus job 1, which is 2. So 28 plus 2 is 30. And the one which I marked here in blue color, right? So that's the elapsed time. The total time in completing the 5 jobs in 2 machines is 30 minutes. So that's basically the elapsed time or the optimal time based on this sequencing, right? Say the sequencing. Let's take a look at without sequencing, right? So what is job 1 in time is 0, since it is pretty much the start of that. Then job 1 in time is 5, right? And machine has to wait 5 minutes to get its job done. Then job 1 machine B is 2, it is 5 plus 2 is 7, right? So we will put 5 here. And job 2 is 1 minute, so that will 5 plus 1 is 6. It takes 6 minutes, whereas we cannot put 7 here, right? Say yeah, we can put 7 here because 7 is greater than 6. Then job 2 is I think machine B is 6, which is 7 plus 6, 13, and which we put it 6 here. What is job 3 duration 1? 9. So that will become 6 plus 9 is 15. And you cannot wait, we cannot put 13 here because 15 is greater than 13. So we will be putting it 15 here. Then what is job 3 machine B? Job 3 machine B is 7. That will become 15 plus 7 is 22. Then we have to come here. It's the job 4. It is 15. It's the initial. Then it is plus 8 plus 3, right? So plus 3. This 18. Pretty much you can give 22 here. Pretty much 22. So job 4 machine B is 8. So that will become 30. And here it is 18. And job 5 is 10. So this will become 28. And it's 30 here. And the job 5 without the sequencing is 34. So which means that the elapsed time without the sequencing is 34, whereas with the sequencing is 30. So that's why it is an optimal time. So you save 4 minutes time. Like say this is something like a theoretical example, but if you do a real practical example, even a minute saved, an hour saved is very crucial in a real-time operations. So that's why we follow sequencing by Johnson's algorithm without being put like this entire sequence, like in this case, right? The next thing will be the ideal time. So ideal time for machine A and ideal time for machine B, right? So you can even ignore this because it itself will take care, because we will be looking into, we will not make any computation for this, right? So that's why the machine A cannot be ideal, because it is a starting machine, and machine B only can be ideal. But the end wait, this is called, it cannot called ideal time. It is thus the end wait time. Say the total operation is 30 minutes, whereas machine A operation gets over by 28 minutes itself. Say 30 minus 28 is 2 minutes. Say the 2 minutes, once the machine A performs, it has to wait, correct? So the entire operation takes, as a slot, it's a single slot. So after the process, the elapsed time is 30 minus the elapsed time of A. This is the total elapsed time or elapsed time of B. This is the elapsed time of A. So the total elapsed time minus elapsed time of A will become the ideal time for A. So which means that the machine gets over, the operation in the machine gets over by 28 minutes itself. But however, it has to wait for 2 minutes for the entire slots gets over, both A and B, right? So that's what basically it's 2 minutes. So that's a minimum idle time, right? But whereas if you take a look at here, it is 34 minus 28. This, you see, it has to wait for 6 minutes. The machine, the idle time of machine is 6 minutes. So it's just pretty much higher. So without in sequence, it takes 6 minutes or something like that, right? Next will be the idle time for machine B, right? So the idle time of machine B is that. Here, the initial wait, it has to wait not for, it does not start, machine B does not start at 0, but instead it has to wait for 1 minute. So that 1 minute is accounted here. Okay, I can put it with color. This particular duration is here. So it has to wait for 1 minute. Whereas in here, it is 5 minutes delay. So without the sequence, it has to wait for 5 minutes. It has to wait for 5 minutes. And the next thing is like it is nominal. So 15 and 13, something like this is greater than. This will be checking this condition. If machine B of the previous case is greater than the output of the machine A in the next case or next job. So if it is fine, then there won't be any ideal time. But in this case, if you take a look at this and 22 and 23, so it has an ideal time of 1 minute. So which means that 23 minus 22, which means that the machine, even though it finishes its performance for job 3 at 22nd minute, but it has to wait for the job 5 gets over by machine A by 23 minutes, and 22 minus 23, or just an absolute difference between 23 and 22 is 1. So that's why we have got 1 here. And same way, 27 here and 28 here, and it is probably, the variation is 1 minute. So in total, it is 3 minutes. Like 1 plus 1 plus 1, it takes 3 minutes. The idle time in machine B, whereas idle time in machine A is 2 minutes. Without the sequence, if you take a look at here, like 13 and 15 is fine. Then 22 and 18, it's also fine. 30 and 28 is also fine. So there won't be any ideal time at all. However, the initial waiting time is 5 minutes. So 6 plus 5 is 11 minutes, whereas the total ideal time by the Johnson's algorithm is just like 5 minutes. Here the idle time of machine B itself is 5 minutes. So that's the significance of sequencing, right? So if you don't do sequencing and you straight away get into the allocations, then we'll be finishing the job by 34 minutes. Not only that, the idle times of machine A and B are pretty heavy, right? Say this is one slot. Remember, in a case of a line production, where you want to produce the entire entity in a mass sector, in a mass way. So even a 4 minutes per slot can amplify to 1,000 slots. So it will be an enormous thing, and it will be a disaster to the particular industry or particular organization, right? So that's why we follow this sequencing, right? Right. So this is a simplified example of sequencing. I'll just do a quick recap. First, we'll have the given problem with the different durations of that particular job in machine A and B. Then we use Johnson's algorithm to sequence that. So we'll be taking this particular sequence. So you can even remove this. After the final stage, it's more or less a sequence rather than for machine B and machine A, because it involves both machine A and machine B. Then that sequence is taken and put it in this particular tabular form, in which we have got machine A in time and out time, and machine B time in and time out. And then we calculate the ideal time for machine A and ideal time for machine B. Right. So this is a typical example. Right. So are there any doubts in this? I think there will be an idle time here because it finishes by 13 and ends by I think it's 2 minutes. Yeah. So it will be not 6 plus 5, it is 7 plus 6, which is 13 minutes, which is pretty heavy. Fine. All right. So are there any questions? All right. So since there's any question,